Hello everyone, welcome to this video. This is the session number 3 of the introductory course on electromagnetic design of SRMs, and from this video we will start the analytic design of the motor. The aim is to develop this Excel file for analytic design of the motor. I prepared this Excel file before, and we will review the equations behind each cell for the analytic design of the motor. So, like other courses, I categorized the variables in this Excel file in separate columns, right? Design variables divided into these two categories, independent, dependent, and we have these variable types. Detailed explanation is available on other courses also. You can refer to those videos, especially for induction motor design course. We discussed this slide and also the electromagnetic design procedure in detail. The Excel file is based on this categorization. So, the analytic design starts by calculation of direct dependent variables. The first variable is the output torque. This is our aim. We are going to design this SR motor. The rated output power is 0.75 kilowatt, and this is the rated speed. So we can calculate the rated output torque, the electric torque that the motor should deliver at its continuous operation, right? Full load operation. Here you can see the rated torque of the induction motor mentioned in this datasheet. When we fed the motor with the 50 Hz frequency, the rated torque is 5.1 Newton meters. And what is the value for the SR motor? The value should be slightly lower because we keep the value of output torque the same but increase the mechanical speed. We consider it the synchronous speed, right? So here is the equation. This is the angular mechanical speed. Omega m is equal to 2 pi times RPS, and RPS is equal to RPM divided by 60. So this is the output power of the motor, and this is the RPS, RPM divided by 60. Also, here we have omega m, 2 times pi times RPS, and the output torque is the output power. The unit here is kilowatt. We should multiply it by 1000 divided by omega m, which is equal to 4.8 Newton meters. So our design, right, should be capable to generate this output torque for the rated current, right? So this is the first calculation, and we calculated the desired value of the output torque. How we can calculate other dependent variables? The input power is equal to the output power divided by the desired efficiency. So we didn't design and analyze the motor yet, but we should assume a value for efficiency and do design versus that, and then analyze the motor, create the finite element model, and calculate the real value of efficiency. So this is the desired efficiency, and after the design, we have the calculated efficiency and we compare. Can we satisfy, right, our desired value or not? So we have this loop, right? We assume these numbers, do the design, and then compare the design, the available design, by the assumed numbers at the first stage of the design. Here I have the desired efficiency is 72.1, the same as this induction motor's IE1 efficiency for the full load. So the input power is equal to the output power divided by the desired efficiency. Here I implemented this equation. This is the real input power, 1.04 kilowatt. And the next variable is the average terminal current, right? When we have the input power and also we have the terminal voltage. So the input power is equal to the terminal voltage or DC link voltage times the average value of terminal current. So the average value of terminal current is equal to the input power divided by the DC voltage. Here I change this number 564 volts, and the average value of terminal current is 1.84. Let's compare this number by the RMS value of the current of the benchmark induction motor. This is the rated current in the case of a star connection, the RMS value of the terminal current, and in a star connection is the same as the phase current, is equal to the 1.88. This is the RMS value. And here is the average value of terminal current. So this is a good comparison. And when we have this terminal current, we can go for other variables. Here we have an important parameter. This is KIT, a number that should be specified by the designer. What is this number and what is the concept behind this variable? Here we have ideal phase currents. Ideal phase currents and the summation of these waveforms results a constant value. This is a DC value. But in real case, we don't have this situation. In the real case, we have this kind of currents. When we excite the phase A, we don't have immediate rise in the value of current. We have a rise time, then we have current chopping, and then we turn off the switch, and we have this turn off time, right? So this is the real case. And to get the same torque, to get the same output power, we know that the average value of this waveform should be the same as this waveform. So we have this terminal current. This is the real case for the phase A, and I define this important variable. If you consider this as the peak value of the phase current, and this is the average value of terminal current. So we define KIT as peak value of the phase current divided by average value of the terminal current. So this equation here, KIT, is the peak value of the phase current divided by average value of terminal current. This fraction is higher than 1. Yes. So when we set this parameter correct, we can do the motor sizing correct, right? So this is important. And we have this number here, KIT. I consider it here equal to 1.7. So when we consider a value for KIT, we can calculate peak value of the phase current. Peak value of the phase current is KIT times the average value of the phase current, which is this one. So according to these waveforms, when we know the value of phase current and peak value of phase current, we can calculate the RMS value of the phase current, right? If we consider these waveforms and use this equation to calculate the RMS value, the RMS value of the phase current will be equal to the peak value of the phase current divided by SQRT of M. And I implemented this equation also here. The RMS value of phase current is equal to 1.81 amps. And here also is the definition of the KIT. So when we know the phase current, we can calculate coil current, right? The coil current, peak value of coil current is equal to peak value of the phase current divided by NP. And RMS value of the coil current is equal to the RMS value of phase current divided by NP. NP is the number of parallel paths in the winding. In this case, in this example, we have 2 coils in each phase. So we can connect these 2 coils in series. In this case, the number of parallel paths is equal to 1, or in parallel. In this case, the number of parallel paths is equal to 2. Similarly for other combinations. So here is the value of NP. I want to consider 6 for NS by 4 for the number of rotor teeth, and number of phases is equal to 3. This is the example that I consider. Also, we can consider 8 by 6 or 12 by 8 other combinations. So let's continue by this combination, and later, if we have time, we can try also other combinations. So also here you can see the value of KIT and the value of NP. I considered it equal to 1. And here is the calculation of the peak value of the coil current and RMS value of the coil current. I implemented these 2 equations. So till now, just we calculated some direct dependent parameters. So just by setting the value of DC, link voltage, output power, rated speed, we can calculate these numbers. Now let's discuss inductances that we have in this motor type, right? Review few definitions, inductance definitions. We use these definitions when we develop the output equation of the motor. Here we have the phase A excited and the rotor is in completely aligned position. The number of stator poles is equal to 8 and we have 6 rotor poles, 8 by 6. And here we have on aligned position, you can see the flux lines, distribution of the flux lines. For these two extreme situations, we can plot the flux linkage versus the stator current, the level of the excitation current. So this is the flux linkage, the calculated value of the flux linkage when we increase the stator current. And here is the flux linkage curve for the aligned position. Yes, for the aligned position, the air gap is small and the air gap reluctance is low. And when we excite the phase A, we have immediate increase in the value of flux linkage. Then we have the saturation, and this is the saturation region. So this is the LAU. This is unsaturated aligned inductance. This is the saturated inductance. This is the aligned saturated inductance. These are different. This is the total inductance. This is incremental value, right? The slope of this line. But this is the slope of this dashed line. And we have unaligned inductance, LU. So we have 1, 2, 3, 4 definitions for the inductance. And we have these two extreme curves for unaligned position and aligned position. But let's discuss the physical concept behind these two curves. Here we have flux linkage, we have the phase current. In the aligned position, we have this curve. This curve is similar to the HB curve of the electric steel, right? HB curve. Actually, this curve reflects the HB curve of the material, the electric steel. The air gap reluctance is low, and this curve depends on HB curve of the material, doesn't depend on the rotor core and stator core structure, right? Because the value of air gap reluctance is low. So this curve is depending on the material properties. HB curve of the electric steel that we use for manufacturing of the rotor core and the stator core. So if we want to modify this curve, the aligned flux linkage curve, yes, we can modify it by the design, but it more depends on HB curve of electric steel, not the motor geometry. But what about the unaligned curve? Here, as you can see, we have a high reluctance, air gap reluctance, and as long as we increase the level of the excitation current, we don't have much increase in the value of flux linkage because we have a high air gap. And here you can see the value of unaligned inductance is low. We have a straight line. This is a good case, as long as we can the value of unaligned inductance, we can improve the motor performance. So this is the unaligned inductance, flux linkage curve and unaligned inductance. However, this aligned flux linkage curve depends on material properties, but this curve depends on the geometry of the motor, right? Depends on the design of the rotor core. If we don't have a good salience ratio and if we have a bad design, we might have this unaligned flux linkage curve, right? We can have some kind of saturation here. This is not a good design. So the form of this curve is determined by the geometry, determined by optimization of the rotor core and stator core. So this is important. After selection of the proper electric steel, we cannot play with this flux linkage curve to modify, to improve the motor performance characteristics. But when we optimize the structure, we mean modifying this unaligned flux linkage curve. That depends on the geometry. So how much we can optimize the motor, how much we can reduce the slope of the unaligned flux linkage curve. We have this aligned saturated inductance and this unaligned value. As long as we can increase the area between the aligned flux linkage curve and unaligned flux linkage curve, we can generate more electric torque, right? Because we increased the area, we increased the electromagnetic energy, the converted energy, right? So this is important. How much we can optimize the rotor geometry? We can have these cases by optimization. We mean reduction of the unaligned inductance. The best case is when, if I draw a tangent line here, right, tangent line on the saturated region of the aligned flux linkage curve. In optimal case, the unaligned inductance could be equal to the slope of this line. So in this case, we have a good design. Later we will calculate this important characteristic by the finite element method, the ANSYS-Maxwell software. Later we will calculate these two important curves. And when we have this case, this is a good design. When this is in parallel with this line, and this is a bad design. Aligned flux linkage curve and unaligned, right? A high value of LU. This is a bad design. So, yes, by just checking the slopes and comparing the slope of this line and this line, we can guess if this SR motor is optimized or not. So let's review. We have four important values for inductance: LU, LS, LAU, LAS. And we will calculate this important characteristic. We will calculate these inductances and discuss during the finite element analysis of the designed motor. So I think it's a good time to pause here. You can review this video and let's continue the design of the stator core and derivation of the output equation of the motor by the next video. So thanks for watching.